Hello. Determine whether or not the triangle contains a right angle. Well, this is all about the converse of Pythagoras' theorem. Here we're given three lengths in centimeters, 6, 7 and 9. And we're going to determine just from these measurements whether it describes a right angle triangle. So first we'll take the longest side and we'll square it. That's equal to 9 squared, which is equal to 81. And then we take the sum of the squares of the other two sides. Of 6 and 7, so we have 6 squared add 7 squared, that's 36, add 49, that gives us 85. Now if the triangle contains a right angle, it is opposite the longest side. But since the square of the longest side, 81, is not equal to the sum of the squares of the other sides, 85, then this triangle does not contain a right angle. This triangle does not contain a right angle. And this could be useful if you're doing an exam and you're given some lengths of triangles, or you're given a triangle and it's shown the lengths and any other data, and normally it's stated that it's not drawn to scale. You could quickly do a check to determine whether it's a right angled triangle. Here's the next set of lengths, 15 centimeters, 36 centimeters and 39 centimeters. So the longest side squared is equal to 39 squared, which gives us 1521. And the sum of the other sides squared, so that's 15 squared, add 36 squared. This also gives us 1521. So since the longest side, or the square of the longest side, is equal to the sum of the squares of the other sides, this triangle contains a right angle, and it's opposite the longest side. Thanks for watching. I'm Alistair. Bye for now. Hello. Triangle ABC and ABD are isosceles. So ABC is the outer and ABD is this one here on the right. They're both isosceles. So we know that equal, we have opposite angles here are equal for ABC, and for ABD we'll have these opposite sides, these opposite angles are equal, because these two sides correspond and they are equal. So in ABC, these two sides are equal. In ABD, these two sides are equal, meaning these two angles are equal. So we'll go ahead and find for ABC, which will allow us to find A. So if ABC, which is this angle here, is 50 degrees, then that follows that since ABD is 50, therefore AC is also equal to 50 degrees. Now, we have here that this is 50, and we also know that this is 50, but if we look at ABD, these two lengths are the same, meaning this angle, X, is equal to this angle, B. And we know the sum of the angles in any triangle is 180 degrees. So if we take away 50 from this, we have 130 degrees to divide equally between B and X. And that will give us 130 divided by 2, which will give us 65 degrees. So we know both B and X is 65 degrees. So X is equal to 65 degrees. And also B, which we want to find, is equal to 65 degrees. So far we've found 2, A and B. Lastly, C. The sum of the angles in any straight line is 180 degrees. We already said that X is 65 degrees. So to find C will be 180, take away 65, which gives us 115 degrees. So we found our unknowns A, B and C. A is 50 degrees, B is 65, and C 115 degrees. Thanks for watching. Oops, let me just write this clearly. 115 degrees. Thanks for watching. My name is Alistair. Bye for now. Hi, a car is advertised for £3,000. So let's make some notes. Advertised for £3,000. And it's to be sold next month. Tom can afford to pay £2,500. So Tom can pay just £2,500. That's all he can afford to pay. By what percentage will the price have to be reduced so that he can afford the car? Well, he needs a reduction of £500 because it's advertised for £3,000. He only has £2,500. So a difference he has to make up is £500. So they need to reduce the advertised price by £500. But what fraction does that represent, or what percentage does that represent of the original or the advertised price? Well, it's 500 over 3,000. Because it's selling for 3,000, you want to know what fraction or what percentage of it do you need to reduce in order for Tom to be able to afford it, and this is times 100%. And this will give us 1/6, 1/6, which is 16 2/3%. So advertised at £3,000, Tom can only afford 2,500, and so they need to reduce the price by £500, and that as a fraction of 3,000 is 16 2/3%. Here we have a diagram of a triangle that has been cut into a smaller triangle here and a trapezium, and we need to work out the area of the trapezium A, B, D, E. So this shaded part here, and we're given some more measurements. We have this side here, we have the height here, and we're given this. We know these are also, we're given that these are right angles. So what springs to mind when you think about right angled triangles? We have no angles, so this must be a use of Pythagoras' theorem. So first we can go ahead and calculate maybe the area or the side. We can calculate the area of this triangle, but that might not help. But if we calculate the overall area of ACE, the triangle ACE, we should be able to find out what the area of the trapezium is. Well, let's take the first step. We do know that we can actually separate this diagram because we seem to have incomplete information. If we were to find the area of the trapezium, which is half the sum of the parallel sides times the height, we're missing the height. If we were to find the overall size or overall side of this large triangle, we're missing this distance or this length ED. So just like how when you're a kid you take things apart, it's no different in maths. This is how you discover what's going on. So we have the larger triangle. Let this represent the larger triangle. We have C, A, and E. We have 12 here centimeters. We don't have any other information, but on the smaller one we have a little bit more. We have the height at 8 centimeters and this side here at 11. So we have C, B, and D here. Well, this brings to mind that both of these are right angle triangles. So we have a case of similar triangles here. They have their angles are proportionate and also their sides. So let's see what the scale factor is that will allow us to scale from the larger to the smaller. If you look at corresponding size, we have 8 over 12. So scale factor is 8 over 12, which is equal to 2 over 3. And we can check that. If we were to scale from 12 down to 8, we multiply by the scale factor, which is 12 times 2 is 24, divided by 3 will give us 8. So we'll be able to scale down. What else can we calculate from the information you've given? Well, we also know that this triangle, we can actually calculate the side BC, which is something we can use to find additional information. So we can use Pythagoras' theorem. So we have BC squared is equal to 8 squared add 11 squared. This is 64 add 121, which gives us 185. So BC must be the square root of 185. I check this on my calculator. That gives us approximately 13.6 centimeters. Another approach we can take is to find the corresponding side DC on the larger triangle, which is EC. Now we're scaling here. This scale factor allows us to scale from the larger to the smaller. The opposite would be the scale factor 3/2, which is just by calculating from 12/8, which is 3/2. If we were to scale 8 up, you can see that would be 8 3 is 24 divided by 2, which is 12. So we can scale 11 to find this length. So that would be EC be equal to 11 times 3/2, which is equal to 33/2, which is 16.5 centimeters. So this length here is 16.5 centimeters. Now we have the height AE and we have the length EC. What can we calculate? Well, we can calculate the area of the large triangle, and then we can subtract the area of the small triangle, because we have the base, and we know our formula is half the base times the height. So for the larger triangle, area is half base times the height, is equal to a half of 16.5 times 12. That gives us 16.5 times 6. Let's check what that gives us. Which gives us 99 centimeters squared as area. This is 99 centimeters squared. So that's squared, sorry. That's the area of the larger triangle ACE. Now the area of the smaller, so this is the large area of the small triangle, that's equal to half the base is 11 times its height, which is 8. So that's half of 88, which is 44 centimeters squared. So just to visualize what we've done, we've calculated the overall area here of this triangle, and then we also calculated the area of the smaller one, BCD. So if we were to remove this area unshaded from this larger area, we'll have the area ABDE, the area of the trapezium, and that's simply done by subtracting the area of larger, which is 99 centimeters squared, and we subtract 44 centimeters squared. This gives us 55 centimeters squared. is there a way of checking this? Well, you could go about finding out what this length is, ED. We know the overall length is 16.5, and if this is 11, then the difference between them, which is 5.5 centimeters, will give you this length, ED. And then you can use that to calculate the area of the trapezium, which is half the sum of the parallel sides, and we can actually do this mentally. The parallel sides are 8 and 12, which is 20 centimeters. We've just calculated the difference between this length and this length to find that this is actually 5.5 centimeters. So we have the area is half the sum of the parallel sides. So if this is 20, then half of that is 10 times the height. The height here is 5.5 times height will give you 55 centimeters, which confirms that this is correct. So this was a problem of similar triangles. It's a good idea if you can understand this. This is what is called true problem solving. So first we found the overall size, area of the larger triangle, and also we found a scale factor. Before that we found the scale factors that would allow us to move from large to small or from small to large. We found the necessary sides of each triangle, and we were able to find areas of the large and small triangle and subtract the small from the large to get 55 centimeters squared. Thanks for watching this video. My name is Alistair. Any questions are welcome, or comments. Please like, follow, or subscribe for more videos like this. Bye for now.